We now move on to chapter 32. This chapter has a lot of interesting material involving medical applications of nuclear physics, but we don't have time to go into this in detail. But if any of you is interested, you can read the stuff on your own. It's interesting, especially if you're thinking about doing anything in the medical field or life sciences. Anyway, we'll only look at two sections. Let's start with 32.5, which deals with nuclear fusion. Nuclear fusion is a nuclear reaction in which two lighter nuclei combine to form a heavier nucleus. Now, if you're trying to merge two nuclei, they will have to overcome the force of repulsion, the Coulomb force of repulsion between the protons of both the nuclei. So you have to provide energy from the outside in order for that to happen. Typically, fusion fuel can be heated to high temperatures, giving the nuclei sufficient kinetic energy to overcome the repulsion, and then they're able to merge, they're able to fuse. So here is a graph of a graph we have seen before. This is on the y-axis, we have binding energy per nucleon. On the x-axis, you have the atomic number A, the total number of nucleons in the nucleus. So when you fuse two light nuclei to form a medium mass nuclei, you're destroying the mass. It turns out that, as you go from somewhere in between here to higher up, you're merging, you're fusing two lighter nuclei to get a heavier nucleus. So as you go up, the binding energy per nucleon increases. And at the same time, the number of nucleons is increasing. The net result is that because the binding energy per nucleon is greater for the product, for the daughter, the larger binding energy per nucleon is the less you have the. So where does this energy come from? It's taken away from some of the mass. So you have smaller mass as you go up on this graph. And so what happens is some of the mass is being converted to energy. And part of that energy is released in these fusion reactions. So when some lighter nuclei merge to give you a heavier nucleus, there is energy that's released. So it's an exothermic reaction. And as you probably know, it has a lot of practical applications. There are nuclear reactors, nuclear power plants, so it's used to generate electricity. It has also been used for some destructive purposes in building bombs, etc. So in general, when lighter nuclei fuse together to form heavier nuclei, binding energy per nucleon increases, which means some mass is being converted to energy. And some of this energy is released and can be utilized. Some examples of fusion reaction. Now, in addition to humans making these reactions happen, they also occur naturally. So let's look at this. these are some examples of fusion reactions. So for example, here you have two hydrogen nuclei combining to give you deuterium, hydrogen 1 plus hydrogen 1 gives you hydrogen 2. And then in the process, positrons are released and neutrinos. And in this reaction, 0.42 MeVs of energy is released. And then you have the hydrogen fuse with the deuterium that's created here to give you tritium or helium-3. I'm sorry, not tritium, but helium-3 plus gamma rays, and you get 5.49 MeVs of energy. And then finally, helium-3 combines with another helium-3, fuses with another helium-3 to give you helium-4 and two hydrogen nuclei. This is called a proton-proton cycle because you start with two hydrogen nuclei, which are basically protons. And then when you're all done at the end, in the end product, you also have two hydrogens. And then here is another nuclear reaction. So you have two electrons plus four hydrogen nuclei combining to give you one helium-4, and then 6 gamma photons. So you have a huge amount of energy that's released here, and then neutrino. Okay, let's look at problem number 32, in which we have to calculate the energy of fusion energy that's released in a fusion reaction. The techniques for these problems are familiar to us. We've done this before in the context of nuclear reactions. So it's a similar kind of problem. So problem 32 here. Two fusion reactions mentioned in the text are neutron plus helium-3 combining, fusing to give you helium-4 and a gamma photon. And neutron plus hydrogen gives you a deuterium plus gamma photon. Both reactions release energy, but the second also creates more fuel. Confirm that the energies produced in the reactions are 20.58 and 2.22 MeVs, respectively. Comment on which product nuclide is most tightly bound, helium-4 or hydrogen or deuterium. Okay, so let's first calculate the energy. Here's the reaction, neutron plus helium-3. That's the first one in the problem. So you write down E equals the change in mass times c squared, because that's where the energy is being released from. It's the reduction in mass is converted to energy. The initial mass is mass of neutron plus mass of helium-3 nucleus minus the final, which is mass of helium-4 nucleus. So you look up the mass of the neutron in atomic units, which is this number, mass of helium-3 from that appendix that I mentioned before, which is this, and then the mass of helium-4 is that. And then instead of 3 times 10 raised to 8, you multiply by 931.5, which gives you the energy in MeV. So it comes out to 20.58. And then the second reaction in the problem is this one. Basically follow the same procedure, and the energy comes out to 2.24 MeV, so much smaller. And then the question is, which one is more tightly bound? So helium-4 is higher in the binding energy per nucleon graph than helium-2, because the A value increases as you go to the right and the graph rises. So in helium-4, you have a greater binding energy per nucleon, so it's more tightly bound. That nucleus is more tightly bound than hydrogen-2. This is hydrogen-2, not helium-2. Okay. Moving on to section 6, which is about fission. It's a process which is just the opposite of fusion. And these are nuclear reactions in which a heavier nucleus splits into lighter fragments. This can occur spontaneously, which is rare, or it has to be induced, usually by an incident neutron. So you send in a neutron, and that triggers this fission reaction. Here's a typical reaction. You have the neutron combining with the nucleus, and then it's forming fission fragments, so breaking up into these two pieces. And then a certain amount of neutrons are also released in the process. So for example, if you hit a uranium-235 nucleus with a neutron, it breaks up into barium-142 and krypton-91, plus 3 neutrons are also released in the process. And then in a typical nuclear reactor, fission reactor, these 3 neutrons will go on to trigger 3 more of these reactions. These 3 neutrons will combine with 3 more of these uranium-235 nuclei, and then the same process will continue, not just continue, but it'll cascade into more and more neutrons. And that's called a chain reaction. So this is a diagram of the chain reaction involved. So this is your initial neutron here on the left, hitting a uranium nucleus, and then more neutrons are produced, which go on to trigger more fusion reactions and so forth. So this whole thing just cascades. And these smaller pieces are the fission fragment nuclei. The larger one is the uranium nucleus. Okay. Let's see. Now, when you have a certain amount of nuclear fuel, fission fuel, which is basically what's being broken up into fragments. You need a certain amount of critical mass of that fuel in order to sustain a chain reaction. Because if you run out of mass, then the resulting neutrons coming out of the reactions won't necessarily find more uranium nuclei to trigger this reaction. So the reaction can then abruptly stop. So in order to make the chain reaction self-sustaining, you need to have a minimum amount of fuel, a minimum amount of uranium nuclei. And that's called the critical mass. Okay, problem number 43. Let's see. Calculate the energy released in the neutron-induced fission, similar to the spontaneous fission. And the reaction is neutron plus uranium-238 results in breaking up the uranium into strontium-96 and xenon 1. No, it's not xenon. I don't know what that element is. 140 plus there are 3 neutrons released. And they tell you the mass of these, the daughter nuclei. So starting with the energy, and then we have to, this result is about 6 MeV greater than the result for spontaneous fission, Y, etc. Confirm that the total number of nucleons and total charge are conserved in this reaction. Okay, so let's write down this equation and then figure out the energy that's released. Here's the equation. Energy released, again, decrease in mass times c squared. So you have a neutron on both sides of the reaction. So here you only need to include 2 neutrons. And you don't have to write it again here. So mass of uranium is the usual. And you multiply by 931.5 and you get 177.1 MeVs. So this is greater because of the gain of neutron. The question was, this result is about 6 MeV greater than the result for spontaneous fission. So in spontaneous fission, there won't be a neutron coming in from the outside. The nucleus would break apart on its own. So because of this additional neutron in the picture, you get a larger energy. Okay, and then in part C, you have to show the conservation and so forth. So you write down the reaction, making sure you have all the A, Z, and N values. And then if you look at A, the total number of nucleons, 1 here, 238 here, 96 here, 140 here, and 3 here. So 239 on both sides. Total number of protons, which is also charge conservation. So 0 for neutron, 92 for uranium, 38 here, and 54 here, 0 here. And again, 92 equals 92. So that proves the conservation. Okay, that is the end of our discussion of this chapter. We will move on to further topics in the next and the last video.